Hello everyone, I'm Greg Stitt. In this talk we're going to continue looking at how to design AFUs using RTL code, and we're going to start talking about a very important piece of functionality here, which is how you get the FPGA to access the CPU's memory. And the way we're going to do it is by using a hardware abstraction layer that provides a simple DMA interface. If you've watched the earlier presentations, you've already seen one way of establishing communication between a host processor and an FPGA using memory mapped I/O. Now that works just fine and it's easy to implement, but it has the limitation of providing very low bandwidth communication. So it is useful for certain situations. For example, if you just want to access control status registers, or if you want to set some configuration options, basically anything that you just do occasionally is appropriate for memory mapped I/O. However, your data inputs to your AFU are usually going to need access to the host processor's memory, because accessing that memory can provide considerably higher bandwidth, and it is almost certainly going to be necessary to get any successful level of performance out of a pipeline, which is what most AFUs are going to implement. So basically, you want to access this memory anytime you are reading or writing to arrays, or especially if you're doing streaming, you need access to the CPU's memory. Now these slides are going to look at how you can go about doing this, how you can access the CPU's memory from the AFU. And there is an example in the repository. I don't refer to it in these slides, but it will go through a detailed code example of how to do this. It is this DMA loopback example. So it might surprise you to find out that after talking about CCIP for quite a few presentations now, we're not actually going to directly use CCIP to access the processor's memory. Instead, what we're going to do is use a hardware abstraction layer that I created that abstracts away all of the nasty low-level details that you would have to use with CCIP. So ultimately you can use CCIP, but the reality is that it's just too complicated for most users. Basically, only experts are going to be able to figure out exactly how to use it for memory accesses. There's just a bunch of challenges that you have to understand how to deal with, which I'll talk about in a future presentation. But you have to deal with things like converting between virtual byte addresses and physical cache line addresses. You have to choose whether or not to break up your stream of data into cache line requests of 1, 2, or 4. And when you do that, you have to make sure that the requests are aligned with appropriate cache line addresses. One really big issue is that when you read from memory using CCIP, you actually don't get the data back in order. It arrives out of order and you have to reorder it for use in your AFU. And there's a handful of other challenges that you have to solve to use CCIP when accessing memory. So what I've done is created this hardware abstraction layer that provides a much simpler interface for accessing memory. So what I do here is I provide a direct memory access, or DMA interface, which is a very common way for having some peripheral, in this case an AFU, directly access the memory of a host processor. And I'll go into the details of that interface in a few slides, but basically a typical DM interface gives you a convenient way of transferring arrays from a processor into some kind of accelerator or some kind of peripheral. Now, it does sacrifice some of the flexibility that CCIP provides, but it does so to greatly improve the ease of use. And although that flexibility is sacrificed, the interface that I'm going to explain here is going to be sufficient for a large number of use cases. So if you need to access memory, I would recommend starting with this interface, and if it doesn't provide you with something that you need, only then falling back to using CCIP directly. All right, so this slide here shows the DMA Read Interface for the hardware abstraction layer. Now this is a really simple protocol that is very similar to what you would see on most DMA interfaces. So you start off by giving the DMA interface a read address. That is the starting address that you want to start reading from in memory. And that address is a 64 virtual byte address. It's basically the address used by software for the data that you are trying to transfer. You then specify the size of the transfer on the read size signal, and that size is specified in terms of number of cache lines. So in this example here, we'll be reading 3 cache lines starting at start address. And then you assert the read go signal for 1 cycle, and that starts the DMA transfer. So then behind the scenes, the DMA interface will then convert your 1 DMA request into a bunch of CCIP requests, and eventually that data will show up to the DMA interface and it will provide it to your AFU. So when the data is available, the DMA interface shows that by clearing the empty signal. So kind of halfway through this timing diagram, you see empty fall to 0. That means the first cache line from the read request is now available. That data shows up on the read data signal. And then to basically tell the interface that you have read that, you assert the read enable signal for 1 cycle. So if you don't assert read enable, the current piece of data will just stay on read data indefinitely until you do assert read enable. So anytime that empty is 1, you should absolutely not read because there's nothing there that's available. So you see that kind of after cache line 0 is read, there's no data available for 1 cycle. And then empty is 0 again. And here on this example, we assert the read enable for 2 consecutive cycles, and that gives us cache line 1 and cache line 2. We only requested 3 cache lines. So at this point, you see the DMA interface asserts the read done signal just to signify that all of the requested data has now been read out of the interface. All right, so here we have the DMA Write interface. It is somewhat similar to the read interface. So we again start by specifying a start address where we want to start writing data in memory. We put that address on the write address signal. And again, that address corresponds to a 64-bit virtual byte address. It's essentially the address that would be used in software to access that location in memory. We then specify a transfer size on the write size signal. And again, that is specified in terms of the number of cache lines that we want to write to memory. And then we assert write go for 1 cycle. And that starts the DMA transfer. So one difference between the DMA write and the DMA read is that when you start a DMA write, no write actually occurs until you tell the interface to write something to memory. And so you can allow for any amount of time to pass before you actually write something, which is useful because different circuits might not have valid outputs for different amounts of time. So when you do have valid data that you want to write to memory, you assert the write enable signal and you provide the corresponding data on the write data signal. So in this example here, kind of in the middle of the timing diagram, the first cache line that I want to write to memory, I would put on the write data signal, and then I assert write enable for that 1 cycle. And then anytime I don't have valid data to write, I simply set write enable equal to 0. So we see that 1 cycle later. We then have 2 valid writes, so we write cache line 1 and cache line 2 in 2 consecutive cycles by asserting write enable for 2 consecutive cycles. And then in the next cycle, we have another valid output, but we have to be really careful here. So you can't always write whenever you want to. You first have to check to make sure that the full flag is not asserted. So if full is asserted, that means the write interface is not able to accept new write requests in that cycle. So although we have data that we want to write, we can't write it in the current cycle. We have to wait until full is cleared. So 1 cycle later, full is cleared. We're then able to assert the write enable, and then that cache line 3, which is the fourth write in this example, that request gets made to the interface. So our circuit has now written everything that we want to write to the interface because we requested a write size of 4, but that doesn't mean that it's actually shown up in memory. So you'll notice that there's a delay between the last user write request and the write done signal being asserted. So write done is only asserted when the final write request and all other write requests have been actually written to memory. Now, if you don't wait for that write done, that's a little dangerous because if you try to read that corresponding data from memory, it might not actually be there yet, and you might get incorrect results. All right, so this slide really isn't the main point of this presentation. It's really just an illustration of other things you can do with a hardware abstraction layer. So really the main point of this presentation is to show you how the hardware abstraction layer provides a DMA interface that is much easier to access memory than directly with CCIP. What I'm showing here on this slide is that you also don't have to use CCIP's memory mapped I/O interface. So we've already talked about that a lot. It's not that hard to deal with, but I just wanted to show another abstraction you could potentially have to provide a different memory mapped I/O interface. And that's what I'm doing here. So this slide shows a timing diagram for the memory mapped I/O write interface in this hardware abstraction layer. Turns out it's actually identical to the way that CCIP memory mapped I/O worked for writes. It just has different signal names. So again, we have a write enable signal that specifies when the processor is trying to write data into the FPGA. And along with that write enable signal is a write address, which specifies the address that the processor is trying to write into. Along with that address is a write data signal that is the data that wants to be written to the corresponding address. This is basically exactly what we saw with the CCIP memory mapped I/O. I just have a different name here. Everything else is the same also. So write data is again 64 bits, just like it was before. Write address again corresponds to 32-bit words. So that means you have to provide even addresses because we're dealing with 64-bit data. I could have potentially changed that addressing method to have it different from the underlying CCIP, but I didn't really want to confuse people with a separate addressing scheme, so I just left that the same. There is one other restriction that is added, and that is because to get this DMA to work with the hardware abstraction layer, there's a bunch of components behind the scenes that are working, and each of those is sharing part of the memory mapped address space. And so you just have to make sure that the addresses you use don't fall within that address space. So if you look in the CCIP standard AFU system Verilog file, you will see some constants that define what is the address space that you can use within your AFU. Or you can just base yours off the examples that I'm providing. And as long as you aren't using a huge portion of the address space, you're probably going to be okay. So here we have the read interface for the memory mapped I/O in the hardware abstraction layer. And this again is very similar to CCIP, but it's simplified in one way to meet the requirements of most use cases. In fact, it's pretty much identical to the simplified use case we looked at when I first explained memory mapped I/O, in that this interface requires the read data one cycle after the read request occurs. So when I first introduced CCIP, I showed you that if you can implement memory mapped I/O that way with that restriction, it's much easier to implement. This interface here just requires it. So the way it works is that the processor, when it's trying to do a memory mapped read, that is signified by the read enable signal being asserted. On that same cycle, the read address signal specifies what address the processor is trying to read from. Now, the FPGA or the AFU needs to look up the corresponding resource for that address, most likely a control status register of some kind, and it has to provide that data on the next cycle. Now, by enforcing this restriction, it makes the interface simpler than what we saw with CCIP. With CCIP, we actually had to specify when we were responding to the request, and we had to provide a transaction ID. Well, that was required because CCIP allows for the reads to be responded to essentially at any point in time. Since we've eliminated that, we no longer need the transaction ID and we no longer need the valid signal for the response because the response is always one cycle later and they can't be done out of order or anything like that. So it's a little bit simpler. It is less flexible because there are valid situations where doing multi-cycle memory mapped I/O reads is useful. But still, having this restriction supports the vast majority of use cases. Another advantage of this is that it actually makes it, of just using a hardware abstraction layer in general, is that it actually makes your code portable across platforms. So if you had written a bunch of code that was specific to CCIP and you wanted to move your application to a different platform that didn't use CCIP, you would have to rewrite a bunch of your code. Now, if you were targeting a hardware abstraction layer, you wouldn't have to do that as long as that hardware abstraction layer had an implementation on that new platform. So that's another advantage of kind of doing it the way I'm doing here. And of course, if you need to, you can add additional flexibility and functionality to the hardware abstraction layer. I just wanted to keep things simple here for kind of explanation purposes. All right, so now on this slide, we can finally take a look at what this AFU is going to look like when using the hardware abstraction layer. As you can see, its interface looks really simple. It has a clock and a reset, which it's always had, so that's not new. But instead of having any kind of CCIP signal, it just has two other signals. It has a memory mapped I/O signal, which is actually a custom interface that I'll explain in a second. And there's also this DMA signal, which again is a custom interface that provides all of the DMA signals. Now at the bottom of the slide, we see at least part of the definition of those interfaces. So for the memory mapped I/O interface, we see that it has a read data signal and a read address and a read enable and a write data and a write address and a write enable and so on. But by using System Verilog's interface construct, we can kind of collapse all that functionality into just a single interface that we can use with just a single line of code on the AFU's interface. Very convenient, very powerful. On the bottom right part of the slide, we have something similar for the DMA interface. So we see all of those signals that I talked about when I went over the timing diagrams. We see those declared here, and those are all part of the DMA signal that is on the AFU's interface now. So on this slide, we can now look at a simple AFU example that uses this DMA interface. This is somewhat abstract because normally the functionality would be application specific, but it's enough to give you an idea of how you would adapt this to your application. So first, you can see at the top of the slide, we are basically taking some virtual read address that we want to start reading from, and we are assigning that to the DMA's read address input. And then we're doing something similar for the DMA's write address input. So we're giving it the 64-bit virtual address that we used in software when we allocated these arrays. And now we're just transferring it to the DMA's inputs to be able to read and write to memory. Now, because the DMA only handles transferring cache lines, these addresses should be aligned to the beginning of a cache line. But if you don't do that, the DMA will automatically align it. Just realize that if you are not aligning it yourself, you might be doing something wrong because you might be requesting data that's in the middle of the cache line. And this particular DMA interface does not provide that functionality. It leaves it up to you to it gives you cache lines, and then it leaves it up to you to slice up the data in a cache line to grab exactly what you need. All right, and then directly below that, it's basically doing the same thing, but for the read size and the write size. So something in your application determines how many cache lines you want to read from memory. I'm calling that read size here. That gets assigned to the DMA's read size input. Same thing for the write size. Your application has to write some number of cache lines. I'm calling that write size. You assign it to DMA.WriteSize. Next, we need to start both of the read and write DMA interfaces, assuming, of course, that our AFU needs to both read and write to memory. I'm kind of assuming here that you have some input array that needs to be read from memory and an output array that gets written to memory. So in this case, we need to start both the DMA write and read interfaces. And here I'm just doing it with a signal called go, but you would connect that to whatever signal you have that starts your application. And then next, we just need to specify the logic for when we actually want to read from the DMA. So if we look at the DMA.read enable, so first of all, we only want to read from the DMA when it's not empty. Because if we're reading when it is empty, we're just reading junk data. So when it isn't empty, that means there is data available to read, and it's the next element that we requested in the DMA transfer. So we want to read when the DMA is not empty and when our AFU is ready to accept that data. Now, I can't tell you exactly what that means because it is application specific, But basically, if you have a pipeline and that pipeline is installed, then your AFU would be ready in that case. And then just adapt it to whatever your application requires. And then for the DMA write interface, or the write enable, we want to first of all make sure that the DMA is not full. If we write data when the DMA write interface is full, we are going to lose that data, and that's going to cause a lot of problems. So we never want to write when it's full. And then the other situation we want to write, or the other requirement for writing, is that when our AFU has to actually have a valid output. So I'm just calling that output valid, but again, translate that to whatever it means for your AFU. If your AFU is a pipeline, it means that there is a valid output coming out of your pipeline, and you want to write that to memory. And then at the bottom here, I'm reading from the write done signal. I could also read from the read done signal. But assuming we're just reading an input array, doing some processing on it, and writing that to an output array, the read we know will be done before the writes are done. And our entire application, which is done, which is what I'm referring to with this done signal, it is done when everything has been written to the output array. And the DMA write interface tells us when that is done because it will assert the write done signal. So that means that our application is done when the DMA write done signal is asserted. And it's basically that simple. You will of course have to change the starting addresses, the sizes, and the read and write conditions, but everything else for accessing memory with this interface stays exactly the same regardless of what your application is doing. So it is a very simple but yet still powerful way of accessing memory. Now we're going to switch and talk a little bit about the software side of using this hardware abstraction layer and the DMA interface. So one thing you have to be careful with is you can't just declare an array like you do normally in software and have the FPGA access that. So you have to allocate memory that is accessed by the FPGA in a very specific way. So I have an example on this slide that shows you how you would go about creating or allocating a 100-element integer array. So first you have to actually instantiate the AFU. This is just the same AFU class that I've used all along, although it has a few new functions now to work with this DMA. So I instantiate the AFU, and then on the next line you'll see I'm calling this AFU.malloc function. So this malloc is conceptually similar to C's malloc, except that it provides different functionality. So first of all, it's templatized, so you'll notice that you have to specify the type. So here I'm specifying we want to allocate memory for some volatile ints, and then in parentheses we specify how many of those ints we want to allocate. So if we want to create a 100-element array, we put 100 in the parentheses, we specify the type, we say it's volatile int, and we assign that to a pointer of the same type because this malloc will return a pointer to that allocated memory. Now, a few things about this. So behind the scenes, this will keep some data structures that are necessary for the FPGA to be able to access this portion of memory. But that's all hidden from you. Once you have called this malloc function, you can then treat this pointer like it was any other pointer to any other array like you would in software. Now, there is one slight inconvenience to this malloc function, and it is done to ensure correctness. So you're probably not used to using this volatile qualifier. So this is used because what can happen here is that as software is executing, the FPGA can modify the memory contents that were allocated here, and the compiler has no knowledge of that. So the compiler could potentially perform optimizations that are done with the assumption that the memory is not going to change for that optimization. But if the FPGA actually does change the memory, then that optimization actually now breaks the code. So the way that you tell a compiler about that so that it doesn't optimize that code is with this volatile qualifier. So if you want to be 100% safe to make sure the compiler doesn't break the code, you have to use this volatile qualifier anytime you call the AFU malloc function. Now, there is a potentially unsafe workaround that allows you to use non-volatile data. And I added this because once you have a pointer to this data, you have to initialize its contents somewhere, and you're doing that in software almost certainly. And depending on your application, you might have a bunch of libraries that you call that you pass it this pointer and it will initialize the array with certain contents. Well, those libraries weren't defined most likely with parameters that were volatile. And if you pass a non-volatile pointer to a function if you pass a volatile pointer to a function that expects a non-volatile pointer, it actually won't compile because it's basically saying that that function might have been optimized in such a way that would break volatile data. But with that said, there are a bunch of situations where you can use non-volatile data and the compiler will not break it. Now you have to be really careful and your behavior might differ from compiler to compiler, but if it's absolutely critical that you're able to use existing code that uses non-volatile data, then what you can do is just use a different malloc function. So within this AFU class, there is a malloc non-volatile. So you call that function and that allows you to use any type you want. You can use ints, floats, whatever, your own custom classes, and it does not have to have the volatile qualifier like the malloc function did. So again, if you're going to use that, just make sure you test it. You might have to even turn off certain compiler optimizations. I've used it myself quite a few times and never run into problems, but I can come up with hypothetical situations where it would break things. So just use it with care. So now that we have allocated an array that can be accessed by the FPGA, what we need to do is tell the FPGA the virtual address of that array so it knows where to read from in memory. And the most convenient way of doing that is to provide the virtual address of the array to the FPGA using memory mapped IO. So we've been doing this all along for other purposes, but we can do it here. We basically have an AFU.write call where we transfer the data to some control status register. So the slide shows it as an address called MMIO array address. So that's just something in the memory map that corresponds to a register. And we're transferring the virtual address of the input array to that register. Now in your code, the memory map would have this register and you would probably connect that to the read address input of the DMA read channel. And now when you would tell that to go, it has the corresponding read address of this input array. So the thing you need to be aware of here is that the translation to the physical address happens on the FPGA outside of the AFU. So that is one of the things that's very complex to implement. So the software just allocates data, gets a virtual address to that data, tells the FPGA that virtual address, and your AFU just tells the DMA that virtual address, and then behind the scenes, the DMA will convert it to the physical address when actually reading from memory. So this hardware abstraction layer we've been talking about does have some limitations you should be aware of. So when I added this to the repository, I did so as an example of how to abstract away complexity by using a simple interface at the cost of some flexibility. I did not create this with the intention of providing all possible functionality that everyone would need for accessing memory. So there are some limitations you need to be aware of, and these limitations I'm going to mention correspond to the hardware abstraction layer that is provided with the DMA loopback example. For future examples, I may expand on this hardware abstraction layer, so I just want to make it clear that these limitations are for this specific example. They might disappear in future examples. So when using the DMA interface, first of all, it provides a single read and a single write channel. There are DMA interfaces that provide multiple channels so that you can have multiple memory transfers going on at the same time, possibly some with different priorities, things like that. This interface doesn't provide that. Another limitation is that both the read and the write interface are limited to transferring cache lines. If you need to transfer something smaller or bigger than a cache line, then you have to do that translation yourself within the AFU. Adding that functionality to the DMA is something I have planned possibly for a future example, but it's not available in this example. So this DMA does not provide an almost full flag. That is a common piece of functionality for various reasons I won't go into now, but if you're designing for high clock frequencies, you typically don't use almost full flags, you use full flags just so that you have more than one cycle to kind of stall things that are going on in your AFU. Another limitation is that the DMA I provided only provides access to the host processor's memory. It does not provide access to the onboard DDR RAM, although that could be easily added to it. The memory mapped I/O has some limitations also compared to CCIP. That limitation is that I have eliminated the multi-cycle reads, so you have to provide read data one cycle after the read request. But again, that's not a huge limitation for most use cases. It would be easy to expand. I just wanted to give you an example of a simplified interface. Now, if you do need a more full-featured DMA, Intel does provide reference designs for two different DMAs that run on the Intel PAC. They have a lot of functionality, probably most of what you would ever possibly need, but they're also a lot more complex. If you look just at the AFU interface for those DMAs, it is tens, if not hundreds of lines of code. Where if you look at the interface I provided for the DMA in these examples, it's like 4 lines of code. So if you can get away with using the simplified interface that I provide, that's probably your best bet. If you need something that's not provided, then you can fall back to these more complex examples. Just realize that there's going to be kind of a learning curve associated with figuring out that more complex but more flexible DMA interface. All right, just to summarize, in this presentation, we looked at how to access the host processor's memory from within the FPGA. Now, CCIP is what enables this memory access, and it does so with a very flexible interface. But the problem is, or the challenge is, that that interface is just realistically too complicated for non-expert RTL designers to figure out in a short amount of time. It's going to be a significant amount of effort to get that working for typical application requirements. So what I did in this presentation, I presented a simplified hardware abstraction layer that provides a common DMA interface for transferring arrays to and from memory. And the way that worked is you basically give the DMA interface a starting address, you give it a transfer size, you tell it to go. If you're reading, you basically then wait until the interface says that it's not empty, and you assert a read enable signal to basically advance the data in the DMA read interface. And for writes, you do something very similar. You wait until the interface isn't full. You also wait until you have data to write to memory. You then assert the write enable and provide the data. And that's it. Super simple. I showed that the hardware abstraction layer also abstracts away the memory mapped I/O interface. So this new interface wasn't considerably simpler than CCIP. I did it really as an example of just how to create a portable hardware abstraction layer across platforms. But it is slightly simpler, so you may want to use it if you don't want to have to deal with transaction IDs and explicitly responding to read requests and things like that. Now, in a separate presentation, what I will do is explain the underlying CCIP memory accesses that I implemented that are kind of hidden within this DMA interface. For this talk, I really wanted to show you how you can go about accessing memory so that you can start writing applications. And then in a later talk, I'll show you how I went about doing that. And I want to point out that the hardware abstraction layer that I've provided for the DMA loopback example is really just a preliminary version. I will likely expand upon that for future examples to provide additional functionality. Thank you for watching.